In mathematics, the triangle inequality states that for any triangle, the sum of the lengths of any two sides must be greater than or equal to the length of the remaining side. If x, y, and z the lengths of the sides of the triangle, with no side being greater than z, then the triangle inequality states that with equality only in the degenerate case of a triangle with zero area. In Euclidean geometry and some other geometries, the triangle inequality is a theorem about distances, and it is written using vectors and vector lengths, where the length z of the third side has been replaced by the vector sum x plus y. When x and y are real numbers, they can be viewed as vectors in one, and the triangle inequality expresses a relationship between absolute values. In Euclidean geometry, for right triangles the triangle inequality is a consequence of the Pythagorean theorem, and for general triangles a consequence of the law of cosines, although it may be proven without these theorems. The inequality can be viewed intuitively in either 2 or 3. The figure at the right shows 3 examples beginning with clear inequality and approaching equality. In the Euclidean case, equality occurs only if the triangle has a 180 degrees angle and 2 0 degrees angles, making the 3 vertices collinear, as shown in the bottom example. Thus, in Euclidean geometry, the shortest distance between 2 points is a straight line. In spherical geometry, the shortest distance between 2 points is an arc of a great circle. But the triangle inequality holds provided the restriction is made that the distance between 2 points on a sphere is the length of a minor, spherical line segment with those endpoints. The triangle inequality is a defining property of norms and measures of distance. This property must be established as a theorem for any function proposed for such purposes for each particular space. For example, spaces such as the real numbers, Euclidean spaces, the LP spaces, and inner product spaces. Euclidean geometry. Euclid proved the triangle inequality for distances in plane geometry using the construction in the figure. Beginning with triangle ABC, an isosceles triangle is constructed with one side taken as BC and the other equal leg BD along the extension of side AB. It then is argued that angle beta greater than alpha, so side AD greater than AC. But AD equals AB plus BD equals AB plus BC, so the sum of sides AB plus BC greater than AC. This proof appears in Euclid's Elements, Book 1, Proposition 20. Mathematical expression of the constraint on the sides of a triangle. The triangle inequality, as stated in words, literally translates into 3 inequalities. A more succinct form of this inequality system can be shown to be another way to state it is implying and thus that the longest side length is less than the semi-perimeter. A mathematically equivalent formulation is that the area of a triangle with sides A, B, C must be a real number. Heron's formula for the area is in terms of either area expression. The triangle inequality imposed on all sides is equivalent to the condition that the expression under the square root sign be non-negative. Right triangle. A specialization of this argument to right triangles is, in a right triangle, the hypotenuse is greater than either of the two sides, and less than their sum. The second part of this theorem is already established above for any side of any triangle. The first part is established using the lower figure. In the figure, consider the right triangle ADC. An isosceles triangle ABC is constructed with equal sides AB equals AC. From the triangle postulate, the angles in the right triangle ADC satisfy. Likewise, in the isosceles triangle ABC, the angles satisfy. Therefore, and so, in particular, that means side AD opposite angle alpha is shorter than side AB opposite the larger angle beta. But AB equals AC. Hence, a similar construction shows AC greater than DC, establishing the theorem. An alternative proof proceeds by considering 3 positions for point B, as depicted, or B coincident with D, or lastly, B interior to the right triangle between points A and D. This theorem establishing inequalities is sharpened by Pythagoras' theorem to the equality that the square of the length of the hypotenuse equals the sum of the squares of the other two sides. Some practical examples of the use of the triangle inequality: consider a triangle whose sides are in an arithmetic progression and let the sides be a plus d, a plus 2d. Then the triangle inequality requires that to satisfy all these inequalities requires when d is chosen such that d equals of 3, it generates a right triangle that is always similar to the Pythagorean triple with sides 3, 4, 5. Now consider a triangle whose sides are in a geometric progression and let the sides be a, r, r2. Then the triangle inequality requires that the first inequality requires a greater than 0, consequently it can be divided through and eliminated. With a greater than 0, the middle inequality only requires r greater than 0. This now leaves the first and third inequalities needing to satisfy the first of these quadratic inequalities requires r to range in the region beyond the value of the positive root of the quadratic equation r2 plus r minus 1 equals 0, i.e., r greater than phi minus 1, where phi is the golden ratio. The second quadratic inequality requires r to range between 0 and the positive root of the quadratic equation r2 minus r minus 1 equals 0, i.e., 0 less than r less than phi. The combined requirements result in r being confined to the range when r, the common ratio, is chosen such that r equals square root phi. It generates a right triangle that is always similar to the Kepler triangle. Generalization of the inequality to any polygon. The triangle inequality can be extended by mathematical induction to arbitrary polygonal paths, showing that the total length of such a path is no less than the length of the straight line between its endpoints. Consequently, the length of any polygon side is always less than the sum of the other polygon side lengths. Example of the generalized polygon inequality for a quadrilateral: consider a quadrilateral whose sides are in a geometric progression and let the sides be a, r, r2, r3. Then the generalized polygon inequality requires that these inequalities for a greater than 0 reduce to the following: the left-hand side polynomials of these two inequalities have roots that are the Fibonacci constant and its reciprocal. Consequently, r is limited to the range 1, t less than r less than t, where t is the Fibonacci constant. Relationship with shortest paths. This generalization can be used to prove that the shortest curve between 2 points in Euclidean geometry is a straight line. No polygonal path between 2 points is shorter than the line between them. This implies that no curve can have an arc length less than the distance between its endpoints. By definition, the arc length of a curve is the least upper bound of the lengths of all polygonal approximations of the curve. The result for polygonal paths shows that the straight line between the endpoints is shortest of all the polygonal approximations. Because the arc length of the curve is greater than or equal to the length of every polygonal approximation, the curve itself cannot be shorter than the straight line path. The converse of the triangle inequality theorem is also true. If three real numbers are such that each is less than the sum of the others, then there exists a triangle with these numbers as its side lengths and with positive area, and if one number equals the sum of the other two, there exists a degenerate triangle with these numbers as its side lengths. In either case, if the side lengths are a, b, c, the triangle can be placed in the Cartesian plane with the vertex opposite length be it, the vertex opposite length c it, and the vertex opposite length r at the second coordinate of this last vertex is a real number if and only if the triangle inequality is met for all sides. Generalization of the inequality to higher dimensions in Euclidean space. The hypervolume of an facet of an n-simplex is less than or equal to the sum of the hypervolumes of the other n facets. In particular, the area of a triangular face of a tetrahedron is less than or equal to the sum of the areas of the other three sides. Normed vector space. In a normed vector space V, one of the defining properties of the norm is the triangle inequality. That is, the norm of the sum of two vectors is at most as large as the sum of the norms of the two vectors. This is also referred to as sub-additivity. For any proposed function to behave as a norm, it must satisfy this requirement. If the normed space is Euclidean, or, more generally, strictly convex, then if and only if the triangle formed by x, y, and x plus y is degenerate. That is, x and y are on the same ray, i.e., x equals 0 or y equals 0, or x equals alpha y for some alpha greater than 0. This property characterizes strictly convex normed spaces such as the P spaces with 1 less than P less than infinity. However, there are normed spaces in which this is not true. For instance, consider the plane with the one norm and denote x equals and y equals. Then the triangle formed by x, y, and x plus y is non-degenerate, but example norm's absolute value as norm for the real line. To be a norm, the triangle inequality requires that the absolute value satisfy for any real numbers x and y, which it does. The triangle inequality is useful in mathematical analysis for determining the best upper estimate on the size of the sum of two numbers. In terms of the sizes of the individual numbers, there is also a lower estimate, which can be found using the reverse triangle inequality, which states that for any real numbers x and y, inner product is norm in an inner product space. If the norm arises from an inner product, then the triangle inequality follows from the Cauchy-Schwarz inequality as follows. Given vectors x and y, and denoting the inner product as x, y, where the last form is a consequentive, the Cauchy-Schwarz inequality turns into an equality if and only if x and y are linearly dependent. The inequality turns into an equality for linearly dependent and if and only if one of the vectors x or y is a non-negative scalar of the other. Taking the square root of the final result gives the triangle inequality. P-norm. A commonly used norm is the P-norm, where the shear the components of vector x. For p equals 2, the P-norm becomes the Euclidean norm, which is Pythagoras' theorem in n dimensions, a very special case corresponding to an inner product norm. Except for the case p equals 2, the P-norm is not an inner product norm, because it does not satisfy the parallelogram law. The triangle inequality for general values of p is called Minkowski's inequality. It takes the form metric space. In a metric space M with metric D, the triangle inequality is a requirement upon distance. For all x, y, z in M, that is, the distance from x to z is at most as large as the sum of the distance from x to y and the distance from y to z. The triangle inequality is responsible for most of the interesting structure on a metric space, namely, convergence. This is because the remaining requirements for a metric are rather simplistic in comparison. For example, the fact that any convergent sequence in a metric space is a Cauchy sequence is a direct consequence of the triangle inequality. Because if we choose any xn and xm such that d less than epsilon 2 and d less than epsilon 2, where epsilon greater than 0 is given and arbitrary then by the triangle inequality, dd plus d less than epsilon 2 plus epsilon 2 equals epsilon, so that the sequence xn is a Cauchy sequence by definition. This version of the triangle inequality reduces to the one stated above in case of normed vector spaces where a metric is induced via dx minus y, with x minus y being the vector pointing from point y to x. Reverse triangle inequality. The reverse triangle inequality is an elementary consequence of the triangle inequality that gives lower bounds instead of upper bounds. For plane geometry, the statement is, any side of a triangle is greater than the difference between the other two sides. In the case of a normed vector space, the statement is, or for metric spaces, d minus d, d. This implies that the norm as well as the distance function d are Lipschitz continuous with Lipschitz constant 1, and therefore are in particular uniformly continuous. The proof for the reverse triangle uses the regular triangle inequality, and combining these two statements gives reversal in Minkowski space. In Minkowski space, if x and y are both time-like vectors lying in the future light cone, the triangle inequality is reversed. A physical example of this inequality is the twin paradox in special relativity. The same reversed form of the inequality holds if both vectors lie in the past light cone, and if one or both are null vectors. The result holds in n+1 dimensions for any n1.